Let's do section 10.2, page 504, exercise 11, which reads, use graphs to find a Taylor polynomial Pn of x for the function natural log of 1 plus x so that the absolute value of Pn of x minus f of x is less than 0.0001 for all x in the interval from negative 0.5 to positive 0.5. So what we're trying to do is find an n value so that when we take the difference between that order Taylor polynomial and our original function, that the absolute value of that difference is going to be good enough, which we talked about in the last video. So let's start by reminding ourselves what a Taylor polynomial is. And that is the summation from k equals 0 to n for whatever order we're looking at. And we're going to have the kth derivative evaluated at 0 divided by k factorial times x to the k. Now we'll talk about the graphing part of this in a little bit, but basically we're going to need to find a bunch of Taylor polynomials, which means that we're going to need a series of derivatives. So we're going to start off with f of x, which is equal to the natural log of 1 plus x. And we're going to evaluate that at x equals 0. And that's going to give us 0. And then we're going to take that first derivative, which is going to be equal to 1 over 1 plus x, which is also equal to 1 plus x to the minus 1. And when we evaluate that at x equals 0, we're going to get 1. Our second derivative is going to be negative 1 plus x to the negative 2. We're going to evaluate that at x equals 0, and we're going to get negative 1. Our third derivative is going to be 2 times 1 plus x to the negative 3 times x equals 0. I'm sorry, not times x equals 0, but evaluated at x equals 0, and that's going to give us 2. Our fourth derivative is going to give us negative 6 times 1 plus x, now to the negative 4, and we're going to evaluate that at x equals 0, and we're going to get negative 6. I think we're going to go a couple more, maybe out to 7. So our fifth derivative is going to be equal to positive 24 times 1 plus x, now to the negative 5, evaluated at x equals 0, and that's going to give us 24. I'm going to go up here and do our sixth derivative, which is going to give us negative 120 times 1 plus x, now to the negative 6. We're going to evaluate that again at x equals 0, and that's going to give us negative 120. And we're just going to go out one more. So the seventh derivative is going to give us positive 720 times 1 plus x, now to the negative 7, evaluated at x equals 0, and that's going to give us 720. So now we're going to substitute these in, and we'll go to our next screen here, and we're going to end up with 0 plus x minus x squared over 2. And not only am I substituting in for each of these derivatives evaluated at 0, I'm also dividing by the factorials. And you should be pretty comfortable. And if you're not, you can write an extra line in here and fill all of that in. And then I'm going to have plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5 minus x to the 6th over 6 plus x to the 7 over 7. So this, as we said, is my P7 Taylor polynomial. Now, let's talk about how we're going to use graphs to help us solve this. Now, the hint here is how to set up your graphing window. And remember, we're looking for the Taylor polynomial that's going to be good enough. So we're going to want to take that difference between our different orders of Taylor polynomials and the actual function. So our x values should be the interval that we're looking at from negative 0.5 to positive 0.5. And for our y values, we want to take whatever that adequacy level is. So we want to go from 0 to 0.0001, 3 zeros there. And basically what I'm going to do is I'm going to take each order of my Taylor polynomial and I'm going to plot it. And the first one of the functions that doesn't touch the top of the screen is going to be the partial polynomial that's good enough. So for instance, my y1 value, when I plot it in my calculator, is going to be the absolute value, however it is that you plot that, of the function, which is going to be the natural log of 1 plus x, and then I'm going to subtract my first Taylor polynomial, which is just going to be x. And when I plot that, if that absolute value is greater than this, then I'm not even going to see it on my screen. So I'm going to know that it would be my first order, or my n equals 1 polynomial isn't going to be good enough. So then my second function that I'm going to graph is going to be the absolute value of the natural log of 1 plus x, again, minus, and now I'm going to take my next two terms. So I'm going to have x minus x squared over 2. And if that, again, is greater than what my adequacy value is, then I'm going to know that that approximation isn't good enough. And I'm going to keep going, and I'm going to plot all of these differences until I get down to y equals 7, which is going to be that absolute value of the natural log of 1 plus x, which is, again, my f of x, my original function. And then I'm going to subtract my whole polynomial here. And I'm not saying this as I write them down, but you can read them. Plus x to the 5th over 5 minus x to the 6th over 6 plus x to the 7th over 7. And when I plot all of that, what you should find, which is the same thing as I found, is that this is finally less than 0.0001, which means that the P7 polynomial that we've written up here is actually the one that is good enough. It's the approximation that's close enough so that I am below that tolerance limit.